All right, so today we're going to continue our discussion of collision theory. And if you recall from yesterday, we had a graph that looked something like this, although I just made it look a little bit wonky, where we had reactants here and then the products here. This was energy, this was time or progress of the reaction, low energy, high energy. And if you recall, we called this thing the activation energy, and then we had the overall energy of the system. In this case, it was an exothermic reaction, which we remember being called delta H. And the delta H is going to be a negative number in this reaction because it is an exothermic reaction. Now, a very important thing to consider here is that any reaction, while the shape of this curve that you see here will be the same to some degree, it is going to vary according to a whole series of things. So in other words, the time is going to change according to a whole bunch of things that we're going to discuss. So it could be that my curve, while it's still going to be an exothermic curve, it actually may look something like this. It may actually dive off sooner. It may go slower. You actually could have some situations where you have an increase in the activation energy. So while you're going to have the overall exothermic looking curve, you can vary that curve even if you don't change the type of reactants that you're looking at. So let's talk about that. The things that will control or will have an impact on the rate of a reaction. So let's revisit something from yesterday where we were talking about this concept of collision theory. There are two things that I want to make sure that we point out here. For example, let's take a look at what's going on here with A and B. You can see in this situation here, we have the two red parts of the molecule that are smashing together. And as a result, that's going to lead to having no combination, so no reaction will occur because the orientation is off. Whereas if you look at B over here, you can see that we have the red part slamming into the blue part, which in this reaction, this made-up reaction, that is going to, that's also not going to lead to the correct orientation. Whoops, I didn't read that carefully. So what do we need to have here is a situation where the black hits the red part, and when that comes together, then you're going to form the products. Now I want you to notice this in-between state here. Do you recall from yesterday, I talked about the very top of the activation energy. I just made the green star right there. That's where you have what's called the activated complex. And I want you to note here that with this activated complex, you don't have the product that forms. What you have is the convergence of the two reactants, and then a product will form after that, inevitably. So the activated complex is going to be something that exists for an impossibly short period of time before the whole reaction moves towards creating the products. And notice here, the products look very different from the reactants that we started with. And then the last thing that's important to make sure we put into your brains is this idea of energy, because having with collision theory, it's not only orientation, but the energy associated with it. So if you bring these two reactants together and the collision isn't strong enough, then even if the orientation is correct, they will not lead to the activated complex and therefore will not form products. Okay, so we need to make sure that we keep this in the back of our mind, having the correct orientation and the correct amount of energy as we move forward. And don't forget, this has a lot to do, I don't know if I used this as my metaphor last time. Baseball is a perfect example, in particular hitting a home run, because we all understand that you need to put energy into the ball, so you have to swing pretty hard when you make contact with the ball. Even if you have perfect orientation, meaning that you square the ball up, you may not be able to hit a home run if you don't put enough energy into it. So we see here Big Papi swinging pretty hard to hit that ball. Similarly, Big Papi could swing really hard at the ball, but if his orientation is slightly off, maybe the ball is a little bit below the bat, and therefore he'll just ground out to second base, or it's above the bat, in which case he'll pop out. You don't have the right orientation. You really have to get it in the perfectly right orientation with the right amount of energy to be able to send that thing out of the ballpark. Okay, so let me list out first the factors that are involved in determining the rate of a reaction, and then we'll come back and talk about each in turn. All right, so here we have the five major factors that affect the reaction rate: temperature, concentration, surface area, the nature of the reactants, and catalyst. So take a moment to write these down, and then we're going to take a look at each one of these in turn. Okay, so with temperature, and this is one that's probably pretty intuitive for you. If you increase the temperature of the environment going on around a reaction, that's going to increase the rate of the reaction. And we can see with this image here, in the image that I have here on the left, there's heat that's sitting there on a hot plate, so it's keeping that siloam stick nice and warm in warm water. Whereas you can see that in this we have ice hanging out, keeping this cooler. And I think you can see, it's pretty obvious here, that the siloam stick here on the left is much brighter than the one here on the right side. And again, it's because there's a reaction going on that's releasing this light, and when the reaction is in warmer temperatures, it can happen at a much higher rate. Now, why is that? Well, I think you can understand that if you have the particles that are going to be involved in a reaction moving around at a much higher rate of speed, there's going to be a higher chance that one, they collide with each other, and two, that they have enough energy when they do collide to have an effective collision. Okay, and then you have number 3 here, the surface area. And if you increase the surface area while keeping the same amount of volume, so that's actually increasing what's called the surface area to volume ratio of the reactants, that will also increase the reaction rate. And I think, as you can see in these simple schematics here, in A, I have a single big old honkin' block of blue material, whatever that reactant is. And in B, you can see that what I've done is I've broken up that same exact amount of blue material, but I've put it into tiny little bits comparatively, right? And as a result, there is much greater access to many different surfaces, more surface of the blue for the red, so that the red can come in contact with the blue stuff and potentially have a greater chance of having an orientation and energy that will lead to an effective collision. So when you increase the surface area to volume ratio of the reactants, you will also increase the rate because you increase the chances of having those effective collisions. Okay, number 4 here we have the nature of the reactants, which I know sounds vague, but there's not really a better way of putting it. And you should just understand that some reactants are naturally going to combine together in different ways. And there's any number of reasons for that to be the case that have nothing to do with the temperature, the concentration, the surface area, etc. It just is the nature of the reactants themselves. So here I have a chemical equation showing the reaction that lithium has with water. And if you look at lithium, lithium is an alkali earth metal, and actually an alkali metal, sorry. And so any of those metals that will naturally form +2 ions, and they're fairly reactive. And you can see here when I put lithium in to a beaker with water, it bubbles vigorously. And when it bubbles vigorously, the bubbles indicate that it's hydrogen gas that's evolving, and it heats up the water. And so if you were to stick a thermometer in there, you'd see that the water was warmer, and lithium ions and hydroxide ions are also formed. So if I take then another metal that's in the same family of metals, you'd expect that they would be similar in terms of how they react with water. And indeed, they are somewhat similar. If you look at this reaction that I have showing potassium combining with water, it's going to combine in exactly the same way. You're going to produce energy, hydrogen gas, there's going to be an ionization event, etc. However, when you put potassium into water, this is what it looks like. It's a pretty explosive affair. So obviously, the rate of reaction that's occurring there is at a much higher rate than it is when we have lithium here. So sometimes just simply the nature of the reactants involved will determine the rate of the reaction. So catalysts, number 5. Catalysts are chemicals that are not directly involved in the reaction, so they would not be included in as a reactant. But because of their presence, they make reactions happen at a much higher rate. And the reason for this is something that you can see here in this exothermic reaction graph that I've shown here. We've seen these before. So I have reactants here and I have products and we have the activation energy. But you can see that the impact of the catalyst here has lowered that activation energy tremendously. So in a sense, it's not unlike you rolling a ball, trying to roll it up a hill so that it'll then cascade down the hill towards the products. If you can lower the activation energy, it takes much less energy to roll the ball up the hill so that it can continue down to the products. And as a result of that, obviously, you are going to have a much higher rate of reaction. What catalysts tend to do is orient the reactants, whatever they are, in such a way that it makes them come together and have an effective collision. But they also sometimes serve to make a reaction mechanism go in a different direction. So the reaction mechanism changes so that you can get rid of, or not get rid of, but sort of change the rate limiting or rate determining step of a reaction mechanism. They're pretty complex. You can take an entire course on the dynamics of catalysts, so we're not going to go into the details of that here in this chemistry course. Suffice it to say that catalysts simply lower the activation energy to allow for a reaction to occur at a much higher rate than if the catalyst were not there. All right, crew. I'll see you on Thursday because there will not be President's Day. Bye.